Okay, hello students, and this is the last video of the 4 videos while I'm away. This one is on section 6.2 on hypothesis tests. And it's specifically for hypothesis tests for a mean as opposed to a proportion. So let's get started, and I'll share with you the textbook. And again, once again, I would highly recommend that you read these sections in addition to watching these videos. All right, now in section 5.1, when we were looking at hypothesis tests for means, all right, we were not using formulas for the standard error, right? We were coming up with to calculate our p-value, if you remember correctly. To calculate our p-value, we use this formula here. This is called a test statistic. And the numerator of the test statistic is the sample statistic, which would be the sample mean, x bar, minus the null value of the null hypothesis. That would be the proposed or hypothesized population mean, the mean that's in the null hypothesis. So we, again, x bar minus mu, and the denominator is the standard error. Now, in section 5.1, for the standard error, we've typically using the standard error that was on a stack key randomization distribution, all right, sampling distribution. Go to the upper right-hand corner and find the standard error there, and we would use that. And now in this section, we're going completely, in chapter 6 in general, we're going completely away from stack key, and we're using formulas. So we're now going to use a formula for the standard error. Now, the problem with typically with means is that we don't know the population standard deviation. Typically, we don't know it. So the standard error, if you remember way back when, the standard error for as far as the formula is concerned, for a sampling distribution of a sample mean is sigma, the standard deviation for the population, divided by the square root of the sample size. But sigma, the population standard deviation, typically is unknown, so it was suggested that we should substitute S, the standard deviation for that particular sample, the one that we got, right? So we're going to use the S, the sample standard deviation, to estimate sigma. So this formula for our test statistic becomes x bar minus mu naught divided by S divided by the square root of n. And this actually is the definition of a t distribution. That's why we're using a t distribution, because when we substitute S into this formula here, this is an actual t score, or t statistic, as opposed to a z statistic. So in this section, we're going to assume that we do not know the population standard deviation, and that's true. Most researchers don't know it, and we're going to use S in this formula here, and therefore we have to use what we're going to be calculating is a t statistic instead of a z statistic. All right. So that's the big change here. Now, once we have the t statistic, okay, to calculate the p-value, what's going to change now is we're going to use, instead of normal CDF to calculate the p-value, we're going to use t-CDF. And by the way, those of you who have the 83 calculator, you do have t-CDF, all right? So it's not something that needed to be added to your calculator features. Inverse t had to be used in the case of estimating a population mean, right? If the population standard deviation was unknown, for a confidence interval, right? We had to use a t critical value, and that required inverse t. And as you know, inverse t is not there on your 83 calculator. And there's a couple, I know there's a couple students who've already updated their 83 calculators, but I know there's several who have not. And again, I'm going to be posting along with the chapter 6, all of chapter 6, for the means, when we're using the t-distribution, we have to use inverse t. I'm going to post a video, right? This is a YouTube video, which will show you how to program your 83 calculator. Right now, the fact that I was not able to do this for you because of the COVID situation, you'll have to actually do the programming yourself, but it's not a big deal. I learned it from watching the video, and you can watch the video also and just follow it step by step. It'll show you how to program your calculator for this inverse t. And then when we get back into class in person on December the 1st, I will, at that time, will be, if somebody has not been able to do it for whatever reason, then I will update your calculator that day. Make sure you bring your 83 calculator that day in case you were not able to follow the instructions on the video. But I would highly recommend to do it, and then it'll show you how to use it. And then when you do section 6.2, confidence intervals, all right, when you need to use the inverse t, find that t critical value, then you'll be able to do it. All right. Now, if you still have trouble, don't worry about it. Those questions where you have to find the inverse t, you can. There's lots of videos out there that show you how to find that inverse t. So you just have to do a little digging. Now, if you're not able to do section 6.2 confidence interval homework, you can wait on it until I get back, and again I'll show you how to use your 83 calculator with that program to come up with that that inverse t critical value. In this section with hypothesis tests, you don't need inverse t. The only thing you need to use is t-CDF instead of normal CDF, and you have it already on your calculator. So everybody should be able to follow and do this particular section homework. All right. So anyway, so let me stop sharing this for a minute. I want to show you the 6 steps of doing a hypothesis test for a mean. All right, hypothesis test for a mean. So just give me a second here. Stop sharing. All right, so let me just highlight this, and hopefully I'll be able to see it when I share. Yeah, here it is. So this will be posted, this particular PDF. Okay. I don't know why it's showing a little here. So hold on one second, a minute. There we go. All right. So it's a PDF handout. I created this so that you'll be able to follow step by step what you need to do when you do a hypothesis test for population mean. So number 1, you state the null and alternative hypotheses symbolically using the mu, as your population mean. All right, because the hypotheses are all about the population. So here's an example for H naught. The null hypothesis is that mu is equal to 75. The alternative hypothesis, mu is greater than 75. And of course, this would be a right tail test since it says greater than. All right. And that says state assumptions. So that would be the first step, is to write symbolically your null and alternative hypothesis. Now, by the way, and I've seen students do this, I have no idea why they don't write everything out. You have to include the parameter. You have to show the parameter. I've seen students say H naught equal to 75. All right. So when the grading, when we grade this on the core part of the final exam, if you don't put all the parts in here, the mu and the equal to and the 75, just put equals 75, you get 0. All right, I'm just telling you up front, the scoring is 0. There, you don't get partial credit for that. So please put in the proper parameter. H naught here, H sub A, that's of course the alternative hypothesis, mu is greater than 75 in this case. Make sure these numbers match. These two numbers have to match. The equals always in the equals is always in the null hypothesis, and there's only 3 choices for the alternative. You either have greater than, less than, or not equal to. In this case, it's greater than. All right. State assumptions. An assumption that's always stated, and make sure you do this on the final exam, is the sample was randomly selected. All right. It has to state that, but that's one of the assumptions, to do a hypothesis test using the normal distribution, the t distribution, whatever we're using. All right, it's absolutely essential. The second one, it has to do, now this is, we have a hypothesis test about a mean. So it has its own second assumption. Basically, it says if the population parameter is normal, that means if the population itself for that, whatever we're measuring, is normally distributed, right? Height, weight, whatever it is, then automatically the sampling distribution is considered normal. All right, automatically. Okay, and it doesn't matter what the sample size is. It could be sample size of 5, and we assume the sampling distribution is normal also. Now, in many cases, the problem doesn't state this, or it states that the population's distribution is skewed. If it's either unknown or it's skewed, then we have to look at the sample size. And the general rule is if the sample size is at least 30, you consider the sampling distribution to be approximately normal. Now, if you remember when we were doing a hypothesis test for a proportion, section 6.1, it had a different second assumption, right? You have to see if the sampling distribution was normal, but then it had those special formulas, n times p, n times 1 minus p. They both have to be greater than or equal to 10. That's for hypothesis tests for proportions. When we're dealing strictly with means here, there's no proportion, so we're looking strictly at the sample size. Is it at least 30? Now the book, when it discusses this, it says 20 to 50, but all textbooks, almost all other textbooks say 30. So that's a standard that is being taught in introductory statistics courses all over the country. And so that's what we go with. All right, so this video is saying this, I'm saying it, it's 30. So if your sample size is 30 or more, even if the population is unknown, the distribution, the shape of the distribution is unknown, or it says that the population parameter is skewed, then the sampling distribution will be normal if the sample size is at least 30, right? If the population parameter is normal, then we don't have to worry about sample size. The sampling distribution is automatically normal. All right, so let's now go to step number 3 in the hypothesis test. Calculating the test statistic. Now, the first case here says if sigma is known. Now, we will use the Z test statistic if sigma is known. We'll use this formula here. But in section 6.2 for hypothesis test, it doesn't even go into that at all. And also, in the final exam, we make an assumption. It doesn't have to be always there, but at least it seems to be an assumption that sigma is unknown. All right, so if it is known, then we're going to use the Z statistics, just like we use a Z statistic for proportions, hypothesis test for proportions. Let's just look at the left side here, just looking at if we do know sigma, calculator Z, and then what do we do? We plot our standard normal curve, and we plot the Z statistic, Z star, along the curve somewhere. And then we determine, number 1, if it's a left tail test, right tail test, or two tail test, just like we did in StatQ. In this case, well, not in this particular case, but if it's a two-tailed test, okay, that is, if the alternative hypothesis says not equal to, has not equal to zero, then to calculate the p-value, we're going to use one of two formulas here. I'll actually write them all out for you so you see it. We're going to say the p-value is 2 times the normal CDF. And if z star happens to be greater than 0, if it's to the left, to the right of 0, okay. Remember, it's a two-tailed test. So if the z star is positive, then we're going to calculate the p-value as the right tail, the area to the right of that z star. And then we're going to multiply it by 2 because it's a two-tailed test. So that's what they're doing here. Right? So if z star is positive, if you calculate z star in step 3, okay, and it's positive, and it's a two-tailed test, then we're going to use this syntax in our calculator. 2 times normal CDF, and the first number is going to be that number in step 3, the z star. And then we're going to put 1,000. All right, that's good enough as the right endpoint. And 0,1 is our mean and standard deviation because this is a standard normal. Z is a standard normal. If however, when we calculate z star, the test statistic in step number 3, okay, and it happens to be a negative number, then we're going to treat. What we're going to do is we're going to calculate the left tail area. All right, so we're going to find the area to the left of that negative z. All right, and we're going to use this syntax here: 2 times normal CDF, and we treat it as a left tail, negative 1,000, comma z star, comma 0, comma 1. Right, so that's if z is negative. And then, of course, we multiply that by 2. All right, so two-tailed tests, we always multiply by 2. If the alternative hypothesis has less than as the symbol, that's a left-tailed test. And here is our p-value, right? We don't multiply by 2. Normal CDF, negative 1,000, z star 0, comma 1. If it's a right tail test, then we're going to look at the right tail, the area to the right. So the p-value is going to be normal CDF, z star, comma 1,000, comma 0. So everything that's shown here is very clear, hopefully, to you. Hopefully it's clear. We'll do plenty of examples in class when I get back. I'll show you all the different examples of these particular cases. But this is case number 1 when we know that we know what the population standard deviation is. Now, in this section 6.2, it says typically we don't. So we're going to, in this section, strictly look at case number 2 in the examples, where sigma is unknown. We're going to replace sigma with the sample standard deviation of S in this formula, and this becomes T. So that sample statistic becomes a T statistic. Notice that everything looks the same on case 2 as it does for case 1, with one exception, or actually 2 exceptions. Number 1, instead of normal CDF, we're going to use TCDF. And then instead of 0, comma 1 inside the parentheses, we're going to use degrees of freedom. And what is degrees of freedom again? It is the sample size minus 1. Whatever the sample size, subtract 1, that is the degrees of freedom. So for example, the sample size is 100, the degrees of freedom is 99. Sample size is 70, degrees of freedom is 69. Sample size is 33, degrees of freedom is 32. All right, so it's the sample size minus 1. But the structure is the same here. The structure is the same. As you can see, the 2 cases where T star is greater than 0 and less than 0 for our two-tailed test. All right. And the left tail test, right tail test, pretty much the structure is the same as case 1. We're using TCDF instead of normal CDF. Now you may ask, what if I make the mistake in the final exam and use normal CDF instead of TCDF? You get points off, unfortunately. It has to be perfect. The syntax has to look this way, right? Okay. So that's it. Now, what's step number 5? Once you've calculated your p-value, this is the normal standard decision rule. If the p-value, and we learned this for chapter 5, right? I think we learned it in chapter 4 too, right? If the p-value is less than or equal to alpha, the level of significance, we reject the null hypothesis if it's less than or equal to. Now, there's some books that say less than or equal to, some books say less than. I think all the examples that we get in all these books are always going to be distinguished. It's either going to be less than or greater than. So don't worry about the equal part here. Some books say less than or equal to, reject the null. To me, that's more logical than just saying less than. And if the p-value is greater than alpha, do not reject. So I believe that in the textbook it says if the p-value is less than, reject, and if the p-value is greater than or equal to, do not reject the null hypothesis. But every case that I'm going to give to you on tests and on the final exam, it won't matter about whether the equal to is here or here. Typically, the p-values are going to be less than alpha or greater than alpha. So don't worry about it so much. But basically, if the p-value is less than alpha, reject the null hypothesis. If the p-value is greater than alpha, not reject. All right, and then there's the interpretation. So for example, if alpha is 5%, it would say something like at the 5% significance level. If we reject the null hypothesis, we would say there is enough evidence. If we do not reject, we would say there is not enough evidence. And then we would say to reject, and then we would have to say what the null hypothesis is. Or another way of saying it is, if we're rejecting the null hypothesis, we would say at the 5% significance level, there's enough evidence to support the alternative hypothesis. We would say that. If we're not going to reject the null hypothesis, so we could say at the 5% significance level, if we're not going to reject it, we would say there is not enough evidence. We could say either to reject the null hypothesis, or we could say to support the null hypothesis. And then we have to say it in the context of the problem. So we don't say null hypothesis, alternative hypothesis. We state exactly what the researcher is trying to do, right? So we have to say it in context. All right, and that's what I'm saying. All right, so this is this particular handout will be posted in Canvas. All right, along with the other 6-step hypothesis test for population mean. And again, watch these videos, watch them again. If you need to watch more than once, watch them more than once. Try the homework. If the homework, if you're struggling with the homework, make sure you don't do more than 2 attempts, so that you can watch what I do in person, in class, when I do my review, right? And then you go back to homework and finish up the homework, all right? In case you're not sure how to do any of these things. All right, so now let's stop sharing. We'll go back to the book and we'll do a couple of examples, and then we'll do a couple of problems in the back of the book, and that will end our meeting. All right, so let's share now the textbook. Okay, let's see if we can find an example. All right. So it says on page 359, there was some data collected to see if the mean body temperature for humans differs from 98.6 degrees Fahrenheit. Right. So this was a particular sample that was taken, and notice here the research is interested if the mean body temperature differs from 98.6. So that means that word differs means the alternative hypothesis will be not equal to 98.6. So the null hypothesis, that's just what we currently think, is that on average, humans have 98.6 as their temperature, core temperature, and then the alternative is that mu is not equal to 98.6. Okay. All right. So anyway, in this particular case, there's a sample of 50 people that were randomly selected from the population, and their core temperatures were measured. And you can see it's most of them are around the 98, 98.6, but there are some ones that are on the high side and on the low side. All right. But on average, the sample mean is 98.26. So when we average the 50 temperatures for the people who were sampled, it came out with 98.26. So that's X bar. So we're going to calculate our test statistic. By the way, step one was to do our null and alternative hypotheses, right? Step two, we have to state our assumptions, okay? And we're going to assume here that the people were randomly selected. So, all right, so that's one of the assumptions. The second assumption is the sample size is at least 30, since there's no information about normality in this problem here, about temperatures being normal, normally distributed. But the sample size is at least 30, it's 50. Then we can assume the sampling distribution is going to be normal. Okay, so we can do all of this, all these calculations. So X bar is 98.26. This is step 3 now. And what is the hypothesized mean? It is 98.6. The denominator is 0.765 is the sample standard deviation. Now, where do they come up with that? Basically, if you entered all of these 50 numbers into your calculator, all right, and went to one variable statistics, you looked up X bar and looked up S. All right, so X bar is 98.26, S is 0.765. All right, so 98.26 minus 98.6 divided by 0.675 or 7.765 divided by the square root of 50, which is square root of the sample size. So I want to show you how to put this into your calculator. It's really important because if you don't put it in right, you're going to get the wrong answer. I've seen many students not do this correctly. So share your screen and share the calculator here. How do we put this t-statistic into the calculator? Right? All right, so what we're going to do is we open up a set of parentheses for the numerator of the t-statistic. I'm going to type in 98.26. Sorry about that. Let's try it again. 98.26 minus, we use minus here, 98.6. Close the parentheses, divide by. Now you should, this is very important, you must use parentheses for the denominator, because the denominator has actually a fraction in it. So whenever we have a denominator having a fraction, we must put parentheses around it. So open up a set of parentheses for the denominator, and the standard deviation is 0.765, and then we divide by the square root. So we do square root of 50. Now, to get that cursor outside of the square root here, we use the right arrow button here, and then close the parentheses. Okay. This is the proper way of typing into your calculator the test statistic. I'm going to hit enter, and that is my test statistic. Now, one thing that you can do at this point because in this particular step number 3, you're calculating the test statistic. You may want to store it into an alpha character, like alpha A. So that's what I'm going to do. I'm going to store the test statistic in alpha A. And hit enter. Okay. So it's now stored in alpha A. And now we can actually use this A in our calculation of the p-value. All right, so let's go back to the problem. And let's go back to the textbook. We're now going to go to step number 4, which is to calculate the p-value. All right, now it's already, you can see it down here, but let's actually do it formally. It is notice the alternative hypothesis is not equal to, all right? Notice that the test statistic is negative. It's negative. So we have a two-tailed test, but the test statistic t is negative. Since it's negative, when we calculate our p-value, we're going to use the left tail to calculate 1/2 of the p-value, and then we're going to multiply it by 2. Because for a two-tailed test, we always multiply by 2. But we use the left tail here, right? So we're going to use that left tail formula. Let's go back to that PDF. Back to the 6th step process here. Show it to you again. Let's go back to step number 4. All right. So step 4 here, we're going to be on case number 2. It's a two-tailed test, and t star is negative. So this formula right here, 2 times t CDF with negative 1,000, comma t star, comma the degrees of freedom. All right. And that's what we're going to put into our calculator. Now we already know that t star is being saved in alpha A in our calculator. Okay. Let's go now down to the calculator. Share the calculator. Okay. So what we're going to do now is we're going to find the p-value, and remember it's two tails, so we're going to say 2 times. Say 2 times, and then we're going to go second VARS where the distributions are, and we're going to scroll down to T CDF. Now remember, alpha is negative. I mean the t statistic's negative, so we're going to put a negative 1,000 here. Right, we're going to treat the area that we're calculating to be a left tail. I'm going to put negative 1,000 here. Negative 1,000. Now, the t statistic is in alpha A, so I'm just going to put alpha A here. And what is the degrees of freedom? Well, the sample size is 50. The degrees of freedom is 50 minus 1, which is 49. Scroll down, hit enter. That's going to be our p-value. Hit enter one more time. 0.0028. So that's our p-value. We round it to 4 decimal places. 0.0028. It's a small p-value. Let's go back to textbook. So now we're going to go to step 5, where we're going to make our decision. Now, when they actually said to do the test, they did not tell you in the problem here what the alpha is. They don't tell you this here. But let's assume alpha is 5%. The level of significance is 5%. Even if we made it 1%, come to the same conclusion. The p-value 0.0028 is much less than alpha 0.05 if the level of significance is 5%. Therefore, we're going to reject the null hypothesis. So that would be step 5, rejecting the null hypothesis. We would write it out that way on our final exam. We would say, since the p-value which is equal to 0.0028, is less than the level of significance, which is 0.05, we reject the null hypothesis. That's what we say in step number 5. Now, step 6 would be the interpretation. And since we're rejecting the null hypothesis, and it's a two-tailed test, we would say, again, assuming alpha is 0.05, we would say at the 5% level of significance, there is enough evidence to support the claim that, well, on average, mean body temperature is different than 98.6. And that is the conclusion. All right. So that's an example of a two-tailed test. All right. All right, let's look at another one. Here is this particular example is an example of a right tail test. All right. So this has to do with Florida lakes. All right. This is actually, there's something was done way back in chapter 2, page 80. There was actually a histogram of levels of alkaline in the lake. And the mean measure of alkaline is 37.5 milligrams per liter. All right. And that's the X bar. And the mean is 38.2. Now, what is the sample size? It says 53 Florida lakes where we measured the alkaline level for those 53 lakes. So that means the sample size is 53. N is 53. X bar is going to be equal to 37.5, and S is equal to 38.2. Okay. All right. So let's look at what the research questions basically see. We want to see if the average level of alkaline level of all Florida lakes is greater than 35 milligrams per liter. All right. So that is going to be the alternative hypothesis. The null hypothesis is mu is equal to 35. All right, so what is our test statistic? Again, the only thing that's given in the problem is the sample standard deviation, nothing about the population standard deviation. So we must use the T statistic. Now, step 1 is the null and alternative hypotheses. Step 2, of course, is our assumptions. Again, we're going to assume here that these 53 lakes were randomly selected from all the lakes in Florida. And the second assumption is because the sample size is bigger than 30, we have 53 lakes here. Even since we don't know anything about whether the lake alkaline levels are normally distributed, it doesn't matter because the sample size is greater than 30. We're going to assume the sampling distribution is normal. All right, so we can continue with this. So those are the two assumptions. And then step number 3 is calculating the test statistic. All right, notice it's X bar minus mu in the numerator. Again, if we're doing with a calculator, we put parentheses around these two numbers here. And the denominator is going to be the standard error, which is S divided by the square root of N. And that's what we see in the denominator. Again, parentheses around the denominator. Otherwise, we're going to get an incorrect result if we don't put parentheses around the numerator and parentheses around the denominator. We get T is approximately 0.48. All right, that's our T. And since this is a right tail test, what formula are we going to use? All right, so we have to go back to our formula sheet. All right, PDF. Take a quick look at that. And since it's so again, case number 2, we don't know the population standard deviation. And we're going to perform a right tail test. So we go all the way down here. And we're going to use this as our p-value. This formula here, TCDF. And we're going to use T star, 1000, and the degrees of freedom. Now, T star is going to be what you calculated in step number 3. 1000, you're going to put in there, and then the degrees of freedom is going to be 52, because the sample size is 1 minus the sample size. Or, no, sample size minus 1. So sample size minus 1, so it's 53 minus 1, 52. That's degrees of freedom. And then we'll get our p-value. Let's go back. So you could try it with your calculator, just like we did before. Book. And according to the book here, when you put in a t-statistic is 0.48, and remember, you can, once you calculate your t-statistic, it would be advantageous to you to save it, to store it in your calculator, maybe in alpha A. And then when you go with the TCDF, you just put an A in there instead of the number. But anyway, the p-value is about 0.317. So that's a pretty large p-value. And in most cases, the alpha, the level of significance, is usually nothing more than 10%. But we'll assume 10% in this case here. They don't mention it here, what the alpha is, but if alpha is 5% or 10%, it doesn't matter. P-value is going to be greater than that number. Okay, it's greater than almost all alphas that are going to be given. So we're not going to reject the null hypothesis. All right, we're not rejecting. So in conclusion, we would say something like, at the, let's say alpha is 10%. We would say at the 10% significance level, there is not enough evidence to conclude that the average level of alkaline in Florida lakes is greater than 35. There's just not enough evidence to show that. Okay, and that's an example of a right tail test. Okay, and although they don't show a left tail test here, but there is one in the back of the book here. So I do want to show you an example of a left tail question. So just give me a second here. Let me find one. Yeah. So we're going to actually go to question. Now they do have examples up here without the word problems, right? What are they assuming here? They're saying it, so for example, 6.127, they give you the null and alternative hypotheses. So it's a left tail test. And here's your, and then here are your sample results. They give you the sample mean, standard deviation, and the sample size. Okay. And they want you to do the 6-step hypothesis test. So it's not a word problem, but they're giving you all that information. They say in the body of the question up here, use a 5% level of significance, assume that the underlying distribution is normal. So it doesn't matter what the sample size is. Again, if for step number 2, we're talking about the samples. The first assumption is the sample is a random sample, so it says it here. And the second assumption is if the population is normal, then the sampling distribution is automatic. You could say that. And that's what they're saying. Assume that the underlying distribution is normal. So that's what you would state. Or if the sample size, if they don't state anything about the normality of the population, or again, if the population is skewed, then we must determine if the sample size is large enough. And again, 30 is sort of the break point for that. All right, so in this case, it doesn't matter whether the sample size is 30 or more, because they say that we're assuming the underlying distribution is normal. So here is for example, 6.127, here is a hypothesis test. Mu is equal to 100 is the null. Mu is less than 100 is the alternative. This is a left tail test. All right. And how do we do this one? So actually, I guess we should do an example of each of these without being a word problem. So the null is mu is equal to 100. The alternative is mu is less than 100. We know that's a left tail test. Given X bar is 91.7, sample standard deviation is 12.5, and the sample size is 30. So let's go to our calculator and just, first of all, let's go to our PDF and determine which formula are we going to use for this. So let's go to the PDF. This, of course, would be step. Well, first of all, we need to before we do anything, let's calculate our test statistic. So let's do that first. All right, so that's step number 3 is our test statistic. All right, so we have to calculate this. It is case 2, of course, because we don't have any information about the population standard deviation. The only thing we have is the sample standard deviation. So let's go ahead and do this problem with the calculator. Clear the screen. And again, we'll use parentheses for the numerator of the test statistic. We're going to put in our sample mean as X bar as 91.7. 91.7. We're going to subtract the hypothesized mean, which is 100. Those parentheses divide by, open a set of parentheses. Sample standard deviation is 12.5. Yes. Divide by the square root of the sample size. Square root of the sample size. Notice we put the full sample size in here. You know, subtract 1. Sample size goes in there. We use our right arrow button to get out of the square root. Close the parentheses. Hit enter. There's our test statistic. Notice it's negative, right? And the null hypothesis, the alternative hypothesis, it says less than anyway. So we're expecting a negative test statistic here. All right. All right, now we're going to save this again. We're going to store it in alpha A. All right, so our test statistics in alpha A. And now we're going to do our test. All right, so it is a left tail test since it says mu is less than 100 is our alternative hypothesis. So we don't have to multiply by 2 to find the p-value. We simply go down to TCDF. It has to be TCDF since we're using the sample standard deviation in the test statistic. It is a left tail test, so we definitely want negative 1,000 to be our lower end and A to be upper end. Now, we already have that in there from a previous problem, so it's good. And what is our degrees of freedom? Well, the sample size is 30, and 30 minus 1 is the degrees of freedom, which is 29. So we have to change that. All right, so that's the way it would look on your 83 calculator. Hit enter. Now, let's read through this here, this number that we got here. This is the p-value. Remember, the p-value is a probability. It must be between 0 and 1. It says 5.3 here. Well, if you say it's 5.3 as your probability, you're wrong, because at the very end here, it says e to the negative 4. What does that mean? It means 10 to the negative 4 power. Scientific notation, that's what this is here. So it's 5.3 times 10 to the negative 4. And by the way, if you type that, if you take 5.3 and multiply by 10 to the negative 4 power, you're moving the decimal 4 places to the left. So therefore, you're going to end up with 3 zeros and then 5, 3. And if you want a 1 there to round it, the 0.8 after that to round it, you can. There's your p-value, basically 0.0005, right? Much less than any alpha that we can use. Remember, alpha is supposed to be 0.05, so this p-value is going to be very small, and it's so for step number 4 or 5. This is step 4, finding the p-value. Step 5 is to compare it to alpha. Alpha is 0.05. This is much smaller than 0.05. Therefore, we're going to reject the null hypothesis. Okay. And then let's go back to the book, and we'll do an interpretation. All right, and the interpretation would be something like, well, actually, we can't do an interpretation here. There's no context. All right, we have to actually have a word problem to do an interpretation. But we could say something like at the 5% significance level, there's not enough evidence to support the alternative hypothesis that the mean is less than 100. All right, so that's an example of a left tail test. We do have a right tail test for 6.129 down here. So we could try that one, 6.129. So this is a case where the null hypothesis is mu is equal to 10. And the alternative is that mu is greater than 10. That's a right tail test. X bar is 13.2. That's the sample mean. Sample standard deviation is 8.7. And the sample size is 12. Now remember, they said that we're assuming normality for the population. Therefore, a sample size less than 30 is okay in this case. Right? You can still assume that the sampling distribution is normal. So the two assumptions, step number 2, the two assumptions, that we have a random sample, and the second one is that because the population is normal, the sampling distribution is automatic. That would be the second assumption. All right, step 3 is calculate our test statistics. So we're going to do that next. Calculator. Clear the calculator up. First thing we're going to do is calculate our test statistics. Again, open up a set of parentheses for our numerator. X bar, our sample mean, is 13.2. Minus our hypothesized mean, which is 10. Close parentheses. Divide by. Open up another set of parentheses. And now we have our standard deviation, sample standard deviation of 8.7. Divide by inside that denominator there. And then we're going to put the square root of how many people? 12. Here, let's assume use the right arrow button to get out of the square root. Close the set with parentheses. Hit enter, and that's our t statistic. Notice it's positive. Okay. I'm going to store that in alpha A. Then we store a number. We replace the number that was in there before. All right. And now we're going to do our test. This is a right tail test. To our handout. Look at the formula for that. Case number 2. Yeah. Right tail test. That's the one down here. Notice it says p-value is t CDF, t star, which we stored in alpha A, comma 1,000, comma the degrees of freedom. What is the degrees of freedom in this case here? Now, if the sample size is 12, degrees of freedom is 11. All right. Let's go back to our calculator. Okay. So we don't multiply by 2 for a right tail test. We simply do TCDF. Now the TCDF, enter. Right tail test would mean we would put alpha A in first. Alpha A. And then one positive 1,000 here. And then the degrees of freedom is 11. 12 minus 1 is 11. Go down, hit enter. And there is our p-value, 0.1144. Once again, a pretty large p-value. And since alpha is considered to be 0.05, this p-value is bigger than alpha. So for step 5, we would say do not reject the null hypothesis. Okay, so that would be step 5. And then step 6 would be an interpretation. Based on the context of the problem, we would say at the 5% significance level, there's not enough evidence to conclude that to support the alternative hypothesis. And of course, if it's a word problem, we would know what that is. We would state it in words. Okay, so this is a case of do not reject the null hypothesis. Now let's look one more example here. Go back to the book. Look at 6.131. This is the case of a two-tail test. Notice that for 6.131, null hypothesis is that mu is 500. The alternative is that mu is not equal to 500. Sample mean is 432. The sample standard deviation is 118. The sample size is 75. Now back to the PDF. See exactly what formula we're going to use here. Okay. Well, again, we have to use case two-tailed test, right? And we have to choose one of these two here, depending on whether the t statistic is positive or negative. So let's actually calculate the t statistic. So let's go back to the calculator. Just so that you don't get mixed up, it's good to clear out the calculator when we get into a new problem. So again, this is a two-tailed test, right? So keep that in mind. But we have to calculate our test statistics. So we have to open up a set of parentheses, our test statistic. Our sample mean is 432, that's bar, minus 500 is our hypothesized mean. And we divide by, again, opening up a set of parentheses. Sample standard deviation is 118. Then we divide by square root of 75. Square root 75. Right arrow button. Close parentheses. Hit enter. Negative 4.99 is our test statistic. Okay, pretty large. We're going to, again, store that in alpha A. Okay. And again, let's go back to the find which formula, because it's a negative test statistic for the two-tailed test. So let's go back here. Okay, so we have a two-tailed test, and t star is negative. We're going to use this formula right here: 2 times t CDF, negative 1,000, t star, and the degrees of freedom. All right, so let's go back. Calculator. Okay, and of course it's a two-tailed test, so we have to multiply by 2 times, and we're going to do TCDF. We're going to use TCDF for this. Okay. All right. Now, in this particular case here, we had a negative TCDF, so we're going to use, we're going to calculate that half of the p-value. It's going to be the left tail. I'm going to put negative 1,000. And then we're going to put A here, alpha A. Degrees of freedom. Well, the sample size is 75, so degrees of freedom is 74. Enter. There's a p-value. And once again, it has that E at the very end to -6. So that means we're going to move our decimal point. We're going to take our 3.872 there and move the decimal point to the left by 6 digits. So that will end up having 5 zeros and 3872 after that. 3872. Right? That's wrong, actually. Should be 5 digits, right? If it says e to -6, we move to our decimal point to the left by 6 digits, so we should have 5 zeros. And then 3872. We don't need all those digits, but that's pretty small, really, really small. P-value, that's much less than alpha is equal to 5% or 0.05. We're going to reject the null hypothesis. That would be step number 5. Okay, and then we would say something like at the 5% significance level, there is enough evidence to support the alternative hypothesis that mu is not equal to 500. Again, we would have to put it into the actual words of the problem if we knew the words. All right, so we've done the 3 types of tests there: left tail, right tail, and two tail, without a word problem. Now, if we were going to use a word problem, let's just do a couple of examples of that. A word problem, we'll do a couple word problems, and then we'll call it a day. All right. So let's get back to the textbook, and then we'll pick out a word problem. All right. So let's look at, see if I can find a good one here. 6.135. Let's look at that one. It's a kind of a lengthy question there, but it's okay. No problem. Not getting enough sleep. So this problem says here, my picture away here so you can see this. All right. It says it's generally recommended that adults sleep at least 8 hours each night. One of the authors recently asked some of her students, undergraduate and graduate students at Harvard, how many hours each had slept the previous night, curious as to whether her students are getting enough sleep. And the data are displayed in this figure here. They're using, of course, a box plot. And you could see that this is right skewed, right? You can see because the lower 50% goes from 4 hours to 6 hours, and the upper 50% of the data goes from 6 to 10 hours. So this is a right skewed distribution. All right. Now, we do have to actually assume here, because there was only 12 students that were randomly selected, all right, for the study here. We do have to assume that the population is normally distributed, because the sample size is 12, all right? And this is really not normal looking here. It's not, all right? This is more skewed. So we're going to just have to assume that the population is normally distributed, right? That's one of our assumptions here. And of course, any question that I give to you on an exam, we'll assume that if the sample size is less than 30, that we're going to assume that normal distribution. All right. Otherwise, we can't do the hypothesis test, at least not the way we won't want to. All right, so we have the sample size of 12 here. Okay. It says that this 12 students average 6.2 hours of sleep, so that's X bar, 6.2, and the standard deviation for the sample of 12 students is 1.70. All right. It says, assuming this sample is representative of all of our students, assuming students need at least 8 hours of sleep a night. Remember, that's the null hypothesis. Right. U is equal to 8. Does this provide evidence on average that our students are not getting enough sleep? What do you mean by not getting enough sleep? Getting less than 8 hours, right? That's what means not getting enough. So that's the alternative hypothesis. Mu is less than 8. All right. Okay. That's clear to everybody. So sometimes you have to read the words of the word problem to determine what the alternative hypothesis is going to be. Is it going to be less than, greater than, or not equal to? In this case, it's pretty clear it's less than. Not getting enough sleep means getting less than 8 hours of sleep. All right. So we have all the data that we need, and we can do the hypothesis test here. And we want to see if there's enough evidence to conclude that that students get on average less than 8 hours. All right. So again, we'll assume the assumptions are met. We have our null and alternative hypothesis, and now we're going to do our hypothesis test. So we have to do our test statistic. Notice in this problem here, the only information that's given about the standard deviation is the sample standard deviation, not the population standard deviation. All right, so we'll go to our calculator, and we can just do the whole thing right away, really quickly. Clear the screen. We'll calculate our test statistics, step number 3. We know that our sample mean is 6.2. minus our hypothesized mean is 8 hours. Close parentheses. Divide by. Open up a set of parentheses. The sample standard deviation is 1.7. Divide by the square root of 12 students. All right. And we use our right arrow button to get out of the square root, close set of parentheses, hit enter. And there is our test statistic. It's negative 0.3056. So we're going to store that in alpha A. Okay. Now we'll do our hypothesis test. This is a left tail test. Right. So let's go to our sheet again. Hopefully, once you do a few of these, you'll know exactly what to do without looking at this sheet. It's a left tail test. This is a formula right here. P-value is equal to TCDF. And there we go. Negative 1,000 T star, test statistic, and degrees of freedom. All right. So let's go to our calculator and continue with this problem. Okay. And so we're going to do, again, TCDF. It is the alternative hypothesis that mu is less than 8. So we're going to do a left tail test, just like it's set up here. Negative 1,000 for the lower A, the alpha A, where we have our test statistics stored. And our degrees of freedom is going to be 11, because we had a sample size of 12. There's our p-value. Very big p-value, 0.3827. And if we go back to the book, I don't know if they say anything about the p-value, about the alpha, the level of significance. They don't mention it, but we'll assume here 5%. Doesn't really matter. 0.3827 was the p-value. It's much bigger than pretty much any alpha somebody will pick. So that means we will not reject the null hypothesis. So initially you looked at the 6.2 average for the 12 students. You might think, oh, that looks pretty low compared to 8 hours of sleep. Looks like you would reject the null hypothesis, but in this case you don't. It's actually, there's normal variation here. It's pretty, you could have on average 8 hours of sleep, and then in this case, it's normal variation could be 6.2 hours of sleep as a for a sample of 12. So our conclusion, we would say, is if we used alpha as 5%, we would say at the 5% significance level, there is not enough evidence to conclude that students on average sleep less than 8 hours. Right? In other words, students don't seem to necessarily sleep less than population. Right? So that's it. Doesn't seem like there's any strong evidence there to support the alternative hypothesis. All right. We could also look at 6.137. Look at that as an example. That was what we just did, of course, was a left tail test. 6.137, this one here. Homes for sale. It says this is a data set that's in StatKey. These are houses available for sale in 3 mid-Atlantic states: New Jersey, New York, and Pennsylvania. Right, there's a table right here that shows there's 30 that were randomly selected from each of the 3 states. Okay. And it says here, use this table, the knowledge that within the US, the typical house price when the data were collected was about $287,000. So that is what they're saying basically is that that is the null hypothesis. That mu is equal to $278,000. Now, We're assuming here that the prices are in thousands, so you don't need to put in the 000. You could just say $278,000. So mu, the null hypothesis is that mu is equal to 278. Now it says here, use this table. Now, what is the alternative hypothesis? Well, they actually are writing them as 4 different tests here, 4 different hypothesis tests. So let's look at part A here. Is the average cost of a house in New York significantly greater than 278,000? So that would be mu is greater than 278, right? So that would be the alternative hypothesis. And actually, they're asking the same question in New York, New Jersey, and Pennsylvania. So these are 3 separate hypothesis tests. So if you did New York, then you would, your test statistic would have the mean is 365.3, standard deviation 317.8. You were using New Jersey, you would use that sample mean and that sample standard deviation, 328.5, 158. And Pennsylvania would also have. So basically what they're asking you to do here in A, B, and C is do 3 separate hypothesis tests using the data, use the same null and alternative hypothesis for each of those cases, and see if you're going to reject the null hypothesis or not for each of those 3 states. This is something you might want to try on your own. That is it, okay, for this one here. So see which one, what are the p-values? Assume alpha is 0.05, that's what they say up here, 5% significance level, and calculate each of these p-values and compare it and see if you would reject or not reject the null hypothesis. Question D is, which state shows the most evidence that the state average is greater than 278,000? The one that shows the most evidence would have the lowest p-value. That would be the answer to D. All right, so calculate your p-values. The one that has the lowest p-value of those 3 states would be the one that you would answer for part D. All right, so you're going to try that one on your own. Right, it's a good example to try on your own. And it is a right tail test for each one of those. And then 6.139, here's a very good example here. I'd like to show you this one. This is going to be a two-tail, I believe. This has to do with team batting averages, all right? And so they're printing out some statistics here. The variables batting average, and sample size, mean. This is a sample mean. This is your standard error of the mean. So that would be your, now it's a standard error of the mean. We're not going to use that standard error of the mean. We're going to use the standard deviation. That's the sample standard deviation. So be careful here. Don't use the standard deviation mean. Use the standard deviation here, this last number here, as your sample standard deviation. All right. All right. And then, so that's what you would use. So the mean is 0.25217. Standard deviation is 0.01084. Sample size is 30. So the answer to part A is, how many teams are in the data set? 30. That's your sample size. What's the mean batting average? That's the number under the mean, 0.25217. What is the standard deviation? That's under standard deviation, 0.01084. Okay. It says here, conduct a hypothesis test to determine whether there is evidence that the average team batting average is different from 0.26, 260 batting average. All right, so the null hypothesis is going to be mu is equal to 0.260. The alternative, since it says different from, average that's different from, that's going to be mu is not equal to 0.26. Different from or differ, they always indicate the alternative hypothesis is not equal to. Okay. All right. So So we're just going to, in this particular problem, they give you another one down here, by the way. Second one down here. Just let's look at the first one. We'll answer the part B for that. All right, so we have, again, I'm going to write down the information we have. Sample size is 30. Now, since the sample size is 30, we have no information about whether the population of batting averages is normal, but we have enough, 30, to say that the sampling distribution is normal. The average of those 30 teams is 0.25217. That's going to be X bar, and S is going to be 0.0104. So let's just do this one right here. Ignore the one down here. Just let's do this one. All right. And let's actually go to our calculator. And this is going to be a two-tailed test. So let's go to our calculator and do this one. This will be the last thing we do today. Clear the screen. Calculate our test statistic. X bar, that's our sample mean, is 0.25217. Our hypothesized mean is going to be 0.260, close parentheses, and divide by the sample mean, sample standard deviation is 0.01084, and divide by the square root of the sample size, which is 30, square root of 30. And use the right arrow button, the right arrow button to get out of the square root, close the parentheses, and hit enter. And there's our test statistic. T is equal to negative 3.956 and so forth. We're going to store that in alpha A. For it. And now we're going to do our two-tailed test. Now notice that the T statistic is negative. So let's go again back to our notes, which is going to be a two-tailed test with a negative test statistic. Let's look at it. So that would be this one right here. So T star is less than 0. So this is the one we're going to use 2 times. Remember, two-tailed test, we're going to multiply by 2. And use that one. T CDF, negative 1,000. T star in degrees of freedom. Use that one. Let's go back to the calculator. Okay. And we're going to again do 2 times. Okay. ECDF. Okay. Remember, since T is less than, our test statistics less than 0, we're going to use this form here. Negative 1,000, lower end. It's going to be left tail. A, upper end. We've already stored our test statistic in A. Our degrees of freedom, well, there's 30 of these teams, so we're going to use 29 as our degrees of freedom. Hit enter. That's what it should look like if you were doing it with your 83 calculator. Hit enter. And notice it's a very small p-value here. It's 4.5 times 10 to the negative 4. So again, we move our decimal point to the left by 4. It's going to be 0.0003045. All right. And because that is much less than any alpha that we would choose, and let's see what alpha that they did choose for this problem here. So go back to our all right. It says how many teams. All right. So part B says, well, it doesn't give us our alpha, right? But we'll assume 5% alpha. Even if we assumed a 10% alpha, it doesn't matter. Or 1% alpha, doesn't matter. Our p-value is much less than any alpha we choose. Therefore, we're going to reject the null hypothesis and support the alternative hypothesis. So how would we say it? Let's assume alpha is at 5% significance level. We would say at the 5% significance level, there is enough evidence to conclude that the batting average, mean batting average of all the teams is not equal to 0.260. Right? And that's an example of a two-tip test. All right, and that is it. That's all we'll be doing today. That concludes all of the information from chapter 6. You should do the homework. Again, if you struggle and you're having trouble, just do 2 attempts. Don't do all 3 attempts and leave it, because the chapter 6 homework is not going to be due until, so I think the 1st or 2nd week, sometime in December. So I have the due dates in Wiley Plus, so take a look. But you do have time. So, but you should try it anyway before we meet again in person, right, on December the 1st. All right, so make sure, and then those of you who have the 83 calculator, make sure you watch that video. I'm going to again post a video or post a link to the video, YouTube video, how to upgrade your 83 calculator with a program so it can do inverse T, which is used, by the way, for the section 6.1 hypothesis test, or excuse me, 6.2 confidence intervals. You need the critical value there. You need to use inverse T for those. So section 6.2 confidence intervals. That's where you're going to need to program your computer to do inverse T. So look for that video and watch it, and program your computer, program your calculator. By the way, everything we've done in chapter 6, there will be things that I will show you in person when we get back into class for doing the Excel project, because there are confidence interval functions, there are hypothesis test functions that Excel provides. But we'll talk about that when we get back. Right now, I want you to learn how to use your calculator to do confidence intervals and hypothesis tests, both for proportions and for means. And as far as our tests are concerned, we will not be having any hypothesis tests, or as far as I know, I guess I have to check, but for differences in means or differences in proportions. But I'll check for the final exam. All right, if there is, by the way, I will go over that with you in class for sure. Okay, so that's it for today. I will stop the recording, and then I will see you guys back. Hopefully, if travel works okay with me, on Wednesday, December 1st, is when we meet again in person. All right. Take care, and that's it.